Okay, thank you all for joining us for the next presentation. So I'm delighted to introduce our next speaker from Eirgrid, the Irish TSO, Dr. Cunlay Leo. So Dr. Cunlay is a senior lead engineer at Eirgrid, where he was responsible for conducting techno-economic analysis to facilitate Ireland's energy security and sustainability. With nearly a decade of experience across the European and African energy sectors, Dr. Cunlay integrates technical modelling, economic insights, and policy expertise to drive secure, affordable, and clean energy transitions. So today, Dr. Cunlay will be presenting Eirgrid's perspective on the challenges of forecasting dispatch down in a complex, evolving power system with increasing renewable penetration, and how to facilitate renewable integration through dispatch down forecasting analysis using PLEXOS. So please join me in welcoming Cunlay to the stage. Thank you very much.
Good evening, everyone. This is the final presentation for today, and I understand that everyone is starting to feel tired and lots of information overload today, so I'll try to be as brief as possible. No equations, I promise. So this is the title of my presentation today, Facilitating Renewable Integration Through Dispatch Down Focused Analysis with PLEXOS. So what's the challenge? So for the use case and the case study today, forecasting dispatch down. So dispatch down meaning the intentional reduction of renewable energy generation from what they can actually produce to what they are allowed to deliver on the system. So doing this in a complex, evolving power system amidst increasing renewable penetration. So this is the outline, just the context on the Irish power system, challenge of modeling the power system, how PLEXOS helps, the case study, dispatch down, the results, key summary and conclusion. I've seen some very sophisticated about us slides today, but this is just very simple. Eirgrid, who are we? We're Ireland's TSO. What do? We're responsible for operating and developing the electricity transmission grid to ensure a safe, secure, and reliable supply of electricity now and into the future. Why do we do this? We support European integration, and just to provide some context here, we are guided by some of the European policies and regulations. We also do this to enhance economic growth, enable energy transition for homes, businesses to have access to electricity every day. And we do this by planning and operating the system to allow for enhanced renewable energy integration. And we also do this by continuously engaging with our stakeholders. So context on the Irish power system, over 5 million people. Peak demand sits at around 5.7 gigawatts, mainly concentrated in the load center, the greater Dublin area. An impressive penetration of non-synchronous generation at the moment, about 75%. Wind generation sits at, the commercially operational wind generation sits at about 6.3 gigawatts. And then we have energy storage of about 1.7 gigawatts. And then thermal generation of over 5 gigawatts with interconnection to Wales in the United Kingdom, Greenlink, which just came online not too long ago, and then the East-West interconnector. And also by 2028, we expect the Celtic connecting the south of Ireland to France to come online. So the Irish power system is evolving. The Climate Action Plan is the overarching government's roadmap to climate neutrality. And then shaping our electricity future is the electricity sector's technical and operational roadmap to achieving this. So what's the challenge? So amidst doing all of this, we want to operate the system safely and reliably, but there are lots of things that we need to consider. There's a growing demand, including the growth of data centers. We have grid constraints. we need to achieve the flexibility requirements, renewable energy penetration targets, and we also need to create the right market incentives for the market to be able to continue to incentivize investments to fill in the gaps to fill in the gap for the system challenges, while also limiting cost to consumers. So challenges of modeling the power system. So power system involves thousands of components, nonlinear interactions, generation, transmission, transformers, and the transmission lines and circuits. We need to accurately model the operational policies as well as the market mechanisms. So the operational policies would include the limits and the rules, including the most strong thermal units, the N-1 contingencies, etc. And then the market mechanisms means that system must adhere to the economic bidding principles. So there's a lot of variability and uncertainty on the system. There's increasing penetration of renewables. Demand patterns are also becoming less predictable with distributed energy resources. And then we have forced outages of power system infrastructure, considering things like forced outages of the transmission circuits and generation. And then also there's the need for a good temporal and spatial resolution. So models must capture short-term operational decisions, dispatch, redispatch, long-term planning, including demand evolution, generation and transmission expansion, etc. And then this would allow us to effectively and more accurately access grid constraints and congestion, which is the use case for today. And then also it requires large volumes of high-quality data. And the optimization problem is also very complex. How does PLEXOS help us? So PLEXOS supports system and market modeling in a unified platform, and it can also help us to capture the short-term operational decisions and long-term planning, which was talked about as part of the challenges of representing the power system. And it can also accurately represent some of the physical limitations of the system, such as the ramp rates, the mean up-down times of conventional generation, transmission, interconnection, and also the reserve requirements based on the operational policy in the country. And also helps with simultaneous optimization of multiple energy sources and services, renewable energy generation, battery storage, and DERs. And then just providing a bit of visual and perspective of how we're able to, how PLEXOS helps us with the spatial representation, just showing how we do the modeling in PLEXOS, Ireland and Northern Ireland as a region, then the different markets represented as zones, and then we're more concerned about what's happening in Ireland, so we're able to model the respective node. All of the nodes on the power system in Ireland is modeled here, and all of the interconnecting generation and demand to each node, and the nodes connecting other nodes based on the transmission lines and the impedance associated with those circuits. Okay, this is a PLEXOS conference, so I'm sure everyone knows what PLEXOS does. I pulled that out from a PLEXOS presentation. Some of the use cases of PLEXOS. In our case, transmission and congestion analysis is one of the main use cases, but generally in Eirgrid, there are a few other use cases, and some of my colleagues are also here if you want to learn more about some of the use cases. So connection policy constraint analysis is a particular project that I work on, and I conduct transmission and congestion analysis. And the last presenter talked about the European resources, the European Resource Adequacy Assessment era, capacity and reliability assessment, and IRP and capacity expansion would be some of the two use cases. So I'm going now into the case study for today. So the dispatch down metric. I know that in different European systems, I mean, the nomenclature and the naming convention for like dispatch down might mean different things, but in the Irish case, it means surplus, curtailment, and constraint. So surplus meaning the dispatch down applied for energy balancing when generation exceeds demand and what can be exported through the interconnectors. And then curtailment meaning dispatch down applied to ensure operational limits are met, and constraints due to like local grid issues. So the combination of these three elements gives us the total dispatch down. And within the organization, some of the projects using PLEXOS for constraint analysis or dispatch down analysis are presented here. So on the project that I work on, the Enduring Connection Policy, and another similar project, the Firm Access Run, and it implicitly provides locational signals to renewable energy developers for network development, including projects like the Network Delivery Portfolio, the Transmission Development Plan. It informs cost-effective grid planning and investments. And then on the dispatch balancing cost, which is a very important topic in Europe, I read somewhere, I don't know how true it is, I don't know if you have a German TSO in the room here, I think about 11.8 billion euros is spent for congestion management in Germany. That is very massive. In Ireland, anyways, it's the imperfection forecast for 24-25, I think it's just over 500 million euros. And then policy direction, we have the Tomorrow Energy Scenarios team here, and this project drives and support policy and regulatory prioritization. So going to the most technical slide, bear with me. So dispatch down analysis process, the stage one, generation, the generation profiles for renewables and the properties for the conventional generation are, fed into the model. Then demand, we consider variable demand, which mainly includes like residential and also fixed demand from the manufacturing facilities and the data centers. Feeds into the PLEXOS model. Then the network configurations, all of the connections as they are on the physical system. And then we also include all of the operational limits and then the network limits and rules. So this is fed into, the PLEXOS model spits out the surplus study, which is essentially the generation dispatch and mimics the day-ahead markets. And then we have the PLEXOS API to get out the Python automation, pulling out the data, processing it into an Excel format, and giving us the post-energy balance, which is an intermediate step that feeds into the second study, which is the curtailment study. So the curtailment study mainly takes into consideration the operational constraints on the system, things like the limits of the system non-synchronous generation. And the same process happens. We have the post-curtailment, which feeds into the final output, which considers the network operational limits and rules. And within the PLEXOS environment, the transmission property, you're able to configure or allow the model to take account of the network limits and the n-1 contingency. And then we have the generation redispatch, which considers the surplus, curtailment, and constraint. Then we have the final step here. We pull out the data, which is automated. It reformulates it in the format that we want in Excel. And then we use Power BI Tableau dashboards for visualization. And then we also use Python automation to produce the report. So this is a very important process because the market participants are very much interested in several scenarios because we don't know exactly what's going to happen in the future. There are lots of plans and policies in place regarding what we need to happen to continue to ensure we are operating a safe and reliable system while also taking into consideration the decarbonization imperatives. But at the end of the day, we need scenarios to show us different paths, and the getting a fine balance between the number of scenarios and the provision of insightful information is always very tricky. So using PLEXOS to get out the Python automation ensures that we're able to produce a lot of scenarios within the time mandated by the regulators. So another very important component is the scenario and sensitivity analysis, and PLEXOS helps us a lot here. So at the moment, the industry, we give them the opportunity to come back with a number of scenarios that would be very useful for them. They came back with over 20 scenarios, but we're able to strike a balance, and we settled on about 17 scenarios. So today's power system would include the current network, current interconnection, and the current installed generation, and the potential eventualities for the future could include the forecasted or like committed and contracted generation in the future, the plans for interconnection, and the plans for reinforcement, which is typically included in a document called the Shaping Our Electricity Future. So the results of the dispatch down forecast process, starting with, this is a very busy slide, so I tried to just focus everyone's attention on the red broken box there. So starting with the first red broken box there, it shows the impact of increasing renewable generation. So what's happening there is that the three bars shows increasing renewable generation. So what happens when generation increases for renewables? Ceteris paribus, meaning everything else remaining constant. So we don't consider like the potential operational developments, we don't consider future reinforcements. So what happens is that with increasing renewable generation, if we don't do anything to continue to allow for more integration, dispatch down increases. So the red element there is the dispatch down due to surplus. The amber or orange is curtailment, and then the big share there is constraint. So at the moment, constraint leads as the main element of the dispatch down. But with current plans that we have in terms of the operational policy, that's one. Secondly, also with demand, with increasing demand, with increasing interconnection, flexibility, we expect, and also network reinforcement. That is, adding much more like circuits to improve the alternate flows, which is very critical in an N-1 contingency analysis. And then having all of that means that we are able to reduce, dispatch down as we progress to 2030 and beyond, which is what the purple downward arrow implies. Then the final thing I want to talk about is the future grid. So we expect a lot of offshore to come online on the system. I think at the moment about 5 gigawatts, but again, this is still indicative because the offshore policy is still a bit in a state of flux, it's still changing. But with current assumptions, we expect that surplus is going to dominate the elements of dispatch down forecast in the future. So I have just one slide for the results. So we have the nodes and areas just showing the level of granularity for the calculation of the dispatch down. So we calculate the dispatch down for each node on the network, and this is delineated into the different areas. So this is just a representative dispatch down in Ireland. You don't quote us on it. It's just, I chose one of the scenarios here, and you can see the big red area there. Your guess is as good as mine. That's like where the capital of Ireland is situated. That's the Dublin area. And the reason for this is that there's a lot of generation all over the country. wind and also conventional generation. So what happens is that power flow is always towards, if you did the power flow analysis with PLEXOS and other power flow tools, it's towards the greater Dublin area. And what happens is that the associated circuits around there gets congested and needs to find alternate paths. So the final slide. What was the problem? Forecasting dispatch down in a complex, evolving power system with increasing renewable penetration. And PLEXOS has helped us with better representation of the system. And with scenario analysis, we've been able to get more robust representation of the potential eventualities, and then the computational and the automation capabilities of the organization also helps with more fast and accurate results. So the combination means that we have a reliable and intelligent modeling and analytical process. So this is very useful for all stakeholders, for the system operators. The system operator, it informs cost-effective power system design and investments. The private sector, including developers, investors, it provides signals to them about the locations that are most suitable for investment. And for the regulator and government department, we have one regulator called CRU in short, and then the government department, DECC. It drives and supports policy and regulatory prioritization. And then for every consumer in Ireland, it indirectly impacts them through lower energy costs and higher decarbonization pace. So that's it. I think I kept my promise. So we are good to go. We have 5 minutes, and I can welcome questions. And thank you so much for listening.
So I can, we've got one. Eric.
Hi. Thanks very much for the very insightful presentation. I just have a question about your last point about providing investment signal to the private sector. But I suppose from, I think under the European ruling, that the constraints and curtailment turn down needs to be compensated for, so meaning paid for by consumers.
Yeah.
Do you think the private sector would actually care too much about the turn down, other than the altruistic reason of wasting the renewable energy?
I mean, at the moment, like that, the adoption of the Article 12 and 13 of the EU Clean Energy Package is still a bit uncertain. There are legal issues at the moment in the country. So I wouldn't say it's the direction is at the moment firm. So I think it's still very important. And even if all of the compensation was going to be adopted, my understanding is that it's going to be for redispatch. So that means there's still, risk with respect to surplus. So I think at the end of the day, I think it's still very important, to understand, how much dispatch down would be happening at every every node on the network. So thank you.
Any other questions?
Hi there. Thanks for your presentation. Very interesting. Can you just flip back a couple of slides to the one with the bar charts on it, actually, please? There's a question on the scenarios. Yeah, that one there. Just interested in the high generation and high network with the purple box and the one next to it, high generation, medium offshore. Obviously, total constraints, dispatch down is obviously quite similar between the two scenarios, but obviously the makeup's very different between those two in terms of the blue box and the red between those two. Just trying to understand, have you done any sort of digging into that to try and understand?
Sorry, is it the
high generation,
this
high
and
network?
this?
High generation, high network. With
That's this.
That one there, and the one
Yes.
to the right of it, with that as well. So the summation there is actually quite similar, but the split between the blue and the red is very different between those two there. So just trying to understand, have you done any analysis to actually understand what particular projects or other elements are actually driving those differences?
Okay, that's interesting. To be honest, the scenarios are a bit different because I think the first one says high generation. That means all of the committed and contracted generation with all of the network, whereas this is mainly including offshore. So what happens, so that means the total generation going into this scenario is much higher than this. So what happens is that when there is more offshore in the system, right, we tend to see more surplus, and the way we analyze the work is in a segmented way. So we start with a surplus study. So what happens is that we are already like losing a lot of. So how I want you to see it is the total dispatch down is kind of the most important element, because the breakdown sometimes can be a bit misleading, because if in this scenario we have a lot of surplus dispatch down, then that means there's lower energy going into the curtailment and constraint study, which might make it seem like, for example, in this case, it feels like the constraints are lower, but in real sense, the network here and here are still the same thing. It's just that we've already, because of the energy demand balance, we've already lost a lot of energy at the surplus dispatch down. So what flows into the network is already lower. So I think, yeah, if you think about it that way, yes. So it doesn't mean like that the network is any better here, for example. Yeah. Yeah.
Thank you. If we could all give Kunle